Sikar is going to present her paper entitled SublonK, Sublinear Prover PlonK. Please welcome Shruti, and you can go ahead.
Okay, I'll just use this. Can you hear me? Okay, perfect. So welcome back everyone after lunch. I hope to tell you about our work on like building sublinear PlonK. This is joint work with Arkarai Chaudhary from NTT Research, Sanjam Garg from UC Berkeley, Arushi Goel from NTT Research, and Rohit Sinha from Swirls Labs. So before we see, what is PlonK, what is sublinear PlonK, let's start with a recap of what are snarks. So they are like succinct proof systems, and quick recap of like what they are first. So Alice here wants to prove to Bob that she knows certain witness such that the circuit computation on the statement X and the witness W gives out 1, meaning that it's a legitimate statement from the language. And Bob in this scenario only has access to the statement. And we're in a world where we care about succinctness and efficiency, so they will share something called a common reference string, which would be pre-set up, and in some scenarios they will also share a random oracle. And in addition, we also need to see how to share the circuit description itself, right? So one option would be to give it, but then the verifier compute time and everything depends on the circuit size, and we don't want that. So there's going to be a input independent pre-processing phase where you can think of the circuit being parsed and then like encoded into this prover parameter and a verifier parameter. And given all this, Alice now wants to send across the short proof for the circuit computation giving out 1. So the statement that we have written on the left, Alice wants to give a proof of this. So what does succinctness here mean? Here, as I mentioned, it's a short proof. So the proof size has to be much smaller than the witness length. And in addition, the verify compute time should be much smaller than the computing the circuit itself. So this is what we mean by succinctness here. Non-interactivity in the snarks is clear from what you see. There's just a single round of communication from Alice where she just sends across this proof, and which means anyone can essentially verify. And then arguments of knowledge is like a soundness guarantee, a stronger variant of soundness guarantee, which says that your proof will not be accepted if there is no witness. So if Alice is trying to fool, that's something she should not be able to. And argument of knowledge is a slightly stronger notion where you can say that like you can essentially extract out the witness if there is a proof that verifies. Okay, so good. That's what snarks are about. Okay, I think it swapped the view for some reason. Yeah, I don't know why it's swapping the view.
Maybe go to display and duplicate in the screen and mirror it.
It is in mirror. Okay, it works. Perfect. Yeah, sorry. Okay, so we saw what snarks are. So there are like numerous snarks constructions that you would have come across. So which one do we care about? Today's talk would focus on the specific construction of snarks called PlonK, which has some nice properties. So particularly, it has like constant proof size, and the verifier time doesn't depend on the circuit size at all. It only depends on the statement size, so constant verifier time as well. And the prover time, of course, still grows with the circuit size as with any other proof system. But why PlonK beyond this nice property of constant proof size? There are also other snarks with that. Well, one, it has been widely used in practice. If you think about like the proof size in actual, it'll be a couple of bytes long. And in addition, it has this very nice property that it supports additional custom gates besides your regular AND OR gates. Addition and multiplication, and also lookup gates, which are very important for several applications that you could think of. So this is why we focus on PlonK. But beyond just plugging in PlonK for this any particular circuit computation, what is the kind of bottleneck that you can think of? For that, let's look at an example scenario of trying to build snarks for this very specific computation, which is executing nested ifs. Okay, so it's as it says, it's very clear. This is the tree of all possible things, and the alphabets you can think of like code snippets or a circuit representation of a specific segment. And it's a nested if, which means, let's say, the green highlighted portion is what gets executed and continues to do so. And if you see, only part of the circuit is executed, whereas the entire circuit is much larger. And so specifically, if the height is L, one drawback of directly plugging in an existing snark, something like PlonK, is that your prover compute time typically will grow with 2 power L, which is the size of the whole big circuit. So this is not something you want to do. It's very wasteful because the active circuit is only, of the size L path, which is L by 2 power L is what is active. So you don't want to pay this price. And that's going to be the focus of where we are targeting the problem at. So we need to extend, first of all, this model of compute to beyond nested ifs. That's one example I took. And this is what we first defined in our model, which we call layered branching circuits. So what you can think of this model as is there are n possible, at each step, there are n possible codes or circuits that can be picked out of. And one amongst them gets executed in every step. So there is one that's picked out of these n, and all of these circuits are of the same size S. Okay, so the orange blocks here indicate selecting the relevant code segment during your active phase of execution. And this you end up executing for k steps, let's say. Okay, so the total circuit size here is n times k times S, because every circuit is of size S. And you essentially have the same choice of n segments for each step. Okay. I don't know what's happening. Okay, great. It works. Yeah, so this is how you would view it in the active phase, right? So all the green segments is what gets triggered in the active phase. 1 out of n gets executed at each step. And, you can even ignore the orange blocks and think of them as being somewhat hardwired in this linking that I've done. Like the active circuit itself, the execution itself takes care of the next input that gets triggered and so on. Like you can think of the encoding as taking care of that. So if you see, the active size is of circuit is of size only k times S. And this is where we want to, the prover size ideally should only depend on this. So if you see this model, apart from nested ifs, which is what I showed you, it also captures this very important application of roll-ups in blockchain. So you can think of n, the number of possible choice of codes, to be like the possible transactions to be executed, and at each step, one amongst them, gets executed. So you can think of roll-ups as getting satisfied by this application, by this model as well, which is why this particular model is what we focus on. And the question we ask is, can we build snarks for layered branching circuits where the online prover time only grows with the size of the active circuit, which is k times S? So this is what I promised. And of course, we will allow the prover to do one-time, input independent pre-processing, which of course has to depend on the entire circuit. This would be true. But given that in the online phase, you only want to pay price proportional to k times S. So that's what we ask. And of course, we are not the first people to ask this question. There have been several lines of works that consider different models, different scenarios. In the interest of time, what I can tell you is there are these 4 sort of broad technical areas that have been addressing this problem. So one is like a la carte proof cost. There are a couple of works doing that. Then there is non-uniform IVCs, which also somewhat try to do similar kind of a thing. And then there are Starks and commit and proof snarks, which also have similar kind of ideas of stitching together, these proofs of different active circuits that are being executed. So I won't get into the details. You can look at the paper for comparison or any of these works. But what I can tell you in highlight, right, is if you look at the works highlighted in red here, they all have the disadvantage that the proof size is non-constant, which if you recall from the PlonK is what we picked because we care about having constant proof size. If you look at the work that is highlighted in green, which is Mirage, this is something that has input-dependent prover pre-processing, which is not ideal. because if you have input dependent, you cannot like use it for multiple proof computation. So this is something we don't want to deal with, and it's not advantageous. And then the works that are in the blue make non-black box use of cryptography. So by which I mean here that they need to prove statements of the form that certain hash computation was done correctly, which means that you can only use snark-friendly hash, which do exist in practice, but ideally you want to build a scheme that essentially does not have statements of that form. So we want essentially, to get rid of all these disadvantages. And what we have at the end is, we achieve this online prover time that is only dependent on the active size and logarithmically dependent on the number of possible code chunks. And we do this while achieving all the nice properties from what I listed in the previous, as drawbacks in previous works, which is we are black box in crypto, we have input independent pre-processing, and we have a constant proof size. So this is what we achieve in this work. And we carry on all the nice features that PlonK has, which means we have universal setup, and we also have support for custom and lookup gates, which means you can plug in, your favorite gates in your circuit that you can think of. Okay, so the main idea, which I won't get into, is that we use something called an extension of lookup arguments, and we extend it to something called segment lookup, which helps you do this. And I would urge you to look at paper, or you can come talk to me anytime, and I would be happy to talk more about it. What I want to mention here is there is a concurrent work that came out around the same time as ours, which uses similar ideas and has online prover cost of O tilde ks. And their work is for the setting where k is greater than n. So there is a dependence on ks alone. And they call it tuple lookup, what we call segment lookup here. In terms of, we also have some experimental results which compare with baseline PlonK. So if you just think of like PlonK as the underlying protocol, here we are stitching together multiple PlonK, so how much price you will pay. And this is the proof size and verification cost. Again, details, I urge you to look at the paper. But we have not, in our code, did not optimize for the reducing the number of pairings. And in fact, like there is a follow-up work of ours which recently came out, and they not only optimize the number of pairings, but they have some new tricks and extend it to something called matrix lookup, which helps you add zk. And in addition, also like improves efficiency of the prover time on top of our work. So that's all I had to tell you. And if you have any questions, I'd be happy to take. Thank you.
Thank you very much, Sruthi. Are there any questions?
Thanks, nice talk. So how much are you assuming about like the different branches, I guess, across time periods? Because on the screen you wrote it as like the same C1 through Cn, but can they be different?
So the C1 through Cn, each of them is different, but for every step, they have to be the same, like same set of n instructions.
I see.
Yeah,
Okay.
that's also how the applications use it. It's like fixed set of instructions that you have, and then at each step, one amongst these instructions get executed. That's how, for instance, roll-ups work. So
Okay.
you don't have like different set of n instructions.
Okay, cool. Thanks.
Hey, thanks for the talk. You mentioned that S has to be the same between the sub-circuits. So what if we have a sub-circuit that does not adapt to S? Do we just add like no op instructions?
Yeah, right now, like you'll have to pad or ensure that it's of same size. That's just like because you need to set those parameters for using the correct setup for PlonK. But yeah, right now that's the way you would do.
Makes sense. Thanks.
Hey, thanks for the talk. I just wanted to ask, and maybe this is my unfamiliarity with the work on snarks, but is the type of problem that this proof is able to prove statements about for the circuit sat language, or like can you prove statements about like other types of languages?
So it could be like anything that can be encoded as arithmetic circuits at the end of the day. So yeah, you can think of.
I see. So the proof statements can they like, are they of the form, like, this is a set of inputs that, like,
Yeah.
makes the output be one?
Yes.
I
yes,
see. Okay.
yeah.
Thank you.
Okay, thank you. Okay, last question.
Hi, thank you. Great work. And yeah, I'm quite interested in like, it's like a sublinear prover in Snarks only works for this specific like nested ifs, where you can just generalize to its like
You can generalize. So the
more
model that I
universal
displayed,
way.
yeah, the model I displayed generalizes. Nested ifs is what example I took. You can think of it like a DAG. It could be any. Can generalize the computation to anything. So it is the model captures beyond nested ifs.
So what you are saying is like we can actually like have sublinear prover in doing generating like Snark proofs.
Yes.
Okay.
Thank you.
Thank you. Can we take the first presentation in order? Okay,
Sorry, the second one's ready to go. If we can keep it.
this second one.
Yeah, and then the first one.
Okay.
But then the first
Thank.